Assalamualaikum warahmatullahi wabarakatuh. And hello, my name is Adam Fess, and I'm from the Persatuan Fizik Universiti Malaya, or PERFU. Today, we'll be talking about the 2023 Nobel Prize in Physics with Professor Dr. Raymond Ooi. Professor Dr. Raymond Ooi is a distinguished lecturer at Universiti Malaya for quantum optics and laser sciences. So, Professor, this year's Nobel Prize in Physics was for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter, correct? Okay, so could you give a brief explanation on this groundbreaking work?
This year Nobel Prize was awarded to Ferenc Krauss, Agostini and Wheeler. They are the pioneers in generation of ultrashort intense laser pulses. They have worked on this field for many years, more than 20 years. So it's an important discovery at the frontier of laser physics. For the first time, they are able to generate such a short optical pulse that is able to image the electron dynamics. So we are able to see the electron dynamics at such a short time scale. So this discovery is very timely because now discovery has opened up new applications, including medical science.
Oh, yeah. So like, could you explain how it works, or is that like a very simplified way of how it works?
Yeah, the mechanism can be understood as follows. We come up with an intense pulse that will hit on the atoms. Then it will eject the electron out from the Coulomb interaction. So this process is called photoionization. But it happens very, very fast, and the electron is not fully ionized. The electron will go very far from the nucleus, and it will come back. When it comes back, it hit the nucleus, and this a recombination between positive and negative charges. At this time, it emits high harmonics of radiation. So the high harmonics superpose to form a very short pulse. So there's a broad spectrum of photon involved to generate ultra-short pulse.
Oh, okay. Yeah. So, why do you think this research is important, this specific?
Fundamentally, this is a very important discovery because, as we know from fundamental physics, the electron is a wave, but we do not know how the electron moves in the atom. The classical picture where electron goes around the nucleus like planet going around the sun does not apply at the atomic scale. Quantum mechanically, we know the electron has probability to appear at certain region of space. There is a probability involved, but we do not know how the electron appears, whether it's appearing here and there, the time scale. So by using this ultra-short attosecond pulse, we can learn how the electron appears statistically at different space and at different time. So it will give us better understanding about the probability and the wave function of electron. Yeah. And also it connects with the Heisenberg uncertainty principle. So fundamentally, it's very insightful progress.
Okay. So could you tell me a bit of how this Nobel Prize will affect your work here at Universiti Malaya?
I feel very excited by this discovery. Actually, this field has been very active over the last few years. There were many conferences focusing on ATO. There's one conference named ATO, and almost every 2 years or so they have it. And I attended once in China. So this conference, when I attended, I've learned a lot about the recent discoveries in this. So I have done some work in this theoretically, and also we have the femtosecond laser in our lab, which we bought more than 10 years ago. So this is one of the directions we wanted to go in. So I'm excited with this development, and right now I'm engaged with another project, quantum communication, but I would like to focus on this when I have completed this quantum communication project. So it's interesting and it's at the frontier of optical science.
So like, we're recording at a faster speed, is it? So it's like you get a more clearer image? Is that what I understand?
You're able to resolve the dynamics in time scale.
Like a smaller time scale?
Yes, because in order to see the quantum object, you need to shine something on it. So here you're shining an optical pulse. which is very short time scale. So if the two quantum phenomena is happening, or the electron is jumping here from here to here, we don't know whether it's jumping or it is appear here and appear here. You know?
Oh, we don't actually know
we don't know
how it moves.
Yeah, how it moves. The Schrodinger equation can only predict the probabilistic result only. What's the electron distribution? But we do not know how the electron appear in real time. Whether it follow circular order or is it just random. So by using this attosecond pulse, image it, and then we know how the electron moves.
So this Nobel Prize is focused on the imaging technology of that, like trying to figure out how it moves. It's like a step in the right direction, right? From what I understand.
One of the applications.
Are there other applications?
Yeah, other applications, like there's a field now they coin as optoelectronics. So we are able to probe the electron dynamics in semiconductor devices. So this is one major application in industries. There are also other applications. We know the photoelectric effect. One is the photoelectric effect, how the photon hit on the material, the photoelectron will be ejected, and how fast the photoelectron is ejected. It's very fast, but we don't know how fast. This short pulse, we can get some idea how fast it is. In order to measure shorter phenomena, we need something shorter, and this is the tool at our disposal now.
Do you think this piece of technology will like create like a cascading, like a bunch of other innovations in like many other fields? Do you think it will cause that kind of domino effect?
It's a new tool at the frontier in terms of time scale. It may open up new possibilities, new technology. The future of application in technology is hard to predict. Every time there is new discovery, there is some prospect in the future. It depends on human creativity, how we make use of the technology that we develop. This is something very fundamental. So it's up to somebody creative to come up with new technology. It's like the invention of lasers last time. When laser was invented, there were not many applications. But now you see laser is used
it's everywhere.
In many areas.
Okay, is there anything you want to add?
Before this discovery, people have been thinking of laser plasma acceleration. So it's a small tabletop particle accelerator. They're using a very short pulse, so charged particle can be accelerated. Instead of building big facilities, laser accelerator, we can use ultra short pulse like attosecond to accelerate charged particle. This is one possible application.
So in the future, we won't need like the giant like colliders, is it? Or do we still need those kind of colliders?
There are limitations with this small scale. We still need the giant facility, but maybe certain process, these particle physics processes can be investigated using attosecond pulse.
Okay. So is there anything else?
Tunneling. So we are able to study the electron tunneling, how electron tunneling through barriers, how fast is it? We know it's very fast, but this attosecond pulse can give us some idea.
Okay, doctor. So if we go from the Nobel Prize to Universiti Malaya, how do you think this research will affect your research in Universiti Malaya?
It's a confirmation that what I'm doing, my research field, is in the right direction. It's at something at the frontier. So it's really motivating for me to strive on, and hopefully we can catch up, maybe contribute to this frontier of research. But I alone cannot do this, because as you know, research requires people, manpower, students. So we need more students to engage in this field of research.
What do you think is the future of physics in Malaysia like? Do you think that we should invest more in this field?
Yeah, there are many smart scientists and also researchers. Malaysian can do many things. You see, there are many good intellectuals. They have gone overseas because there are no opportunities in the area of research they are interested in or they excel in. So it is important that we continue to support frontier research in whatever way possible so that we can keep our talents, we can catch up the field of excellence that are really at the frontier one. So if there is no such field and there are people with expertise here, we should try to nurture the talent so that the talent remains here. Otherwise, once the talent goes overseas, we are lost already. So if without talent, the research prospect will be quite difficult. Without fundamental research, we can only do science at a very superficial level. We cannot compete. In order to compete with the international level, we need fundamental research besides innovation. These two must come together.
So, Prof, I actually forgot a question. Maybe you could explain to the viewers what you're doing here at Universiti Malaya. What is your research?
Yeah, my research group called Quantum and Laser Science. So mainly our work is on theoretical, but we also do some experiment with laser interaction. Many topics that involve interaction of photon with atoms, molecules and matter. This is what our research focusing on. There are many names. You can call it quantum optics, quantum nonlinear optics, and then quantum plasmonics, intense laser interaction, also nonlinear laser spectroscopy, and then photonic materials. There is a class of material called photonic band gap material, and now they have extended it to metamaterials or negative index materials. Now the very hot topic is quantum technology, quantum communication, quantum computing. But quantum computing, we can only do it at the fundamental theoretical level, because we are not able to do experiment to build a quantum computer because it requires a lot of financial resource. So this is that we have limitation. So we focus on mainly the theoretical aspect. Once we have the theoretical foundation, then we can go further to experiment. But right now we have funding from the government on the quantum communication. So we are doing theory as well as experiment.
If you want to ask, question to the floor.
I think when I was reading about the Nobel Prize research, right, they're talking about electron dynamics, right? But as you have mentioned earlier, it's the electrons are not really orbiting the nucleus, right? So what's actually moving? What's going on that they are trying to look at?
It's like it could be the electron, like twinkle, like your star twinkle here, twinkle there. At night, if you see there's a firefly, see that here lights up, and then after that, like here lights up. The electron could be moving in this manner, but we do not know how until we have this ultrashort pulse shine to the electron to probe the dynamics. Then we can study the statistical distribution in terms of time and space. Then we can understand better how the electron move.
So the reason we need attosecond pulses is because the rate at which it is twinkling is on attoseconds.
Yes. Yeah, it's an attosecond. So far, is the shortest controllable and man-made phenomena. So if we can control it, we can use it to measure something.
I think you have done previous research in femtosecond stuff as well, right? So what's the difference between that and attosecond?
Yes. So femtosecond is about 1,000 times longer than attosecond, 1,000 times longer. So femtosecond laser has been used to study chemical reaction. So chemical reaction involve the motion of atoms in the molecules. So during chemical reaction, molecule will go from one state to another state, and during this transition, the atomic bond, the bond length will change, right? And this change in the atomic bond length can be measured by using femtosecond pulses. But because atom is bigger, so it moves slower. Now electron is 1,800 times lighter than atom, than proton. So it will move very fast. So now with the attosecond pulse, it's almost perfect to image the motion of electron. I did theory on the photoionization. Photoionization theory was first introduced by Keldysh. The name Leonid Keldysh was a Russian. His work on theoretical ionization rate of electron when you shoot with a laser. So that the theoretical work is very important foundation for us to understand the photoionization rate. So after that, some people extend his work to develop the dynamics of this interaction with intense laser pulse. So there is this so-called Keldysh parameter that will characterize the region of interaction. There are two kinds of interaction. One is multi-photon ionization. One is above threshold ionization, ATI. So these two mechanisms are actually the basis behind the discovery of attosecond pulse. It's an important mechanism. So earlier work, theoretical fundamental work to understand the mechanism, this is very important for the discovery of attosecond. We have extended the theory of Keldysh in our papers. Also another work related to this, we came up with a scheme, a series of petawatt lasers. Superpose the petawatt lasers into a small point. At this point, the intensity can reach to 10 to power 28 watt per meter square. That kind of intensity has opened up new physics. Because why? At this intensity, the vacuum becomes non-linear. You can create particles or antiparticles from vacuum. And there has been some theoretical work in Germany. Max-Planck Institute, they have done theoretical work. But experimentally, we need that laser with such intensity. So I have proposed a scheme to generate this intensity. So these are the main work that I have done related to this intense laser field.
So maybe as a conclusion, do you have any other words to say? Maybe some inspiring words for people who want to enter quantum science, laser science?
First, whoever want to enter this must have passion first, right? Must urge to know, the urge to learn more. So if you have passion, just go in. But you need the fundamentals. You can find somebody in the field of expertise. Somebody can guide you. Then you just go in and learn with enthusiasm and sincerity. Then you can excel.
Okay, so that was all from Professor Dr. Raymond Ooi. If you want to know further, you can people contact you, email you? Yeah, you can find his email on the Expert, and you can, if you have any questions, you can ask him directly, or you can try to ask us on our Instagram page. We'll try to answer with our undergraduate knowledge. Okay, so thank you so much, Professor Raymond.
You're welcome.
We are very honored to have you as our first ever guest for the interview, and hopefully we are able to make this into an successful series. So thank you, Professor Dr. Raymond Ooi.
Thank you. All the best.